Hello everyone. In the last lecture, we have learned two analysis methods for the nonlinear resistor circuits. One is the analytical method. The analytical method seems to be able to get the accurate solution, but as taught in the last lecture, in the process of solving the nonlinear algebraic equations, it needs to use the numerical method, so it also has errors. Another method is the graphical method. The graphical method is very convenient and practical in engineering. But from the implementation process of the graphical method, you can find that the graphical method itself also brings the error inevitably. Since the solution of the nonlinear resistor circuits will inevitably bring errors, is there any way for the modeling of the nonlinear components? This is a new way. This method is a piecewise linear method we will teach today. Okay, let's teach the piecewise linear method of the nonlinear resistor circuits. For the nonlinear resistor circuit shown in the figure, you can see in the first quadrant of the UI plane, its UI relationship is a nonlinear and a smooth curve. Here, the piecewise linear method is a method for establishing the piecewise linear model for such an element. The so-called piecewise linear model is to use a set of polylines to represent the nonlinear curve. So specifically for such a curve, of course, we have many kinds of ways. We can first focus on this area. In this area, the most intuitive approach is to draw such a straight line. Some student may ask that doesn't it have errors in these areas? Yes, it has an error, but we will find later that we will try to make the element working in this section. Then the error can be ignored. For such a straight line past the origin in the UI plane, it is a resistor. So we can model this part as a resistor. Its resistance is tangent A. For the next part, it is relatively difficult. It is the line AB. The line AB has an angle with the horizontal axis. This angle is B. Of course, it also corresponds to a resistor, but according to the Thevenin theorem, we've learned such a straight line corresponds to a Thevenin circuit, which consists of a voltage source and a serial resistor. The resistance of the resistors is tangent B. The value of the voltage source is U0, getting from the intersection between the reverse extension of this line and the U-axis. So we know the corresponding characteristics of line AB are a voltage source and a resistor. The value of the voltage source is U0 and the resistance of the resistor is tangent B. After giving UI features of a nonlinear component, how to get its piecewise linear model? I need to point out that different people may provide different models. That means the number of the segments of the polylines is different. The accuracy is also different too. Of course, the more segments brings the higher precision, but we will find from our discussion later, there exists a trade-off between the accuracy and the conveniency. Return back to our study now. We got the model, so what can we do with it? Let's look at the problem. The nonlinear element is here. You got the piecewise linear model. If you know that the nonlinear element is a resistor, then the circuit is a simple linear resistive circuit. If you know the component is a serial connection of a resistor and a voltage source, then the circuit is a serial connection of two voltage sources and two resistors. The circuit becomes very simple. But the problem is that, how do I know which model to use? Okay, we don't know now. We can guess. This is the most important concept in this lecture. We will guess whether it works in this section or that section. But we don't know. Then we need to verify it. So the method is called the suppose verify method. Okay, let's do the exercise. We look at the problem. This problem is a serial connection of a voltage source, a linear resistor, and a nonlinear resistor. The UI relationship of the nonlinear resistor has been written here. We draw its UI features in the figure. It is divided into two sections. We start from the first section. The first section is the voltage from 0 to 2 volts and the current is from 0 to 1 ampere, it should be a resistor. The resistance 2 over 1 equals 2 ohms. Its condition should be the current is less than 1 ampere or the voltage is less than 2 volts. First, we assume that it works in section 1. It is a 2 ohm resistor, so it should be such a resistor. Now we find its current or voltage. The voltage is easy to solve. We know it is 3.5 volts directly with the voltage divider. Of course, it is larger than 2 volts. So the value doesn't meet the assumption. Next, we assume that it is in this section 2. We assume that it works in section 2. For the section 2, the voltage changed from 2 to 5 volts. The current changed from 1 to 3 amperes. So the resistance must be 1 ohm. This is no problem. But from the line, it should be a Thevenin circuit. There is also a voltage source. So look from the extended line, there is a 1 volt voltage source. So its equivalent model should be like this. Connecting these two circuits and it becomes such a circuit. Then we want to solve the current. What is this current? It can get directly 7 minus 1 over 2 plus 1 equals 2 amperes. This 2 amperes is very good, which satisfies the voltage or current conditions for section 2. It works at this point, which we call it the Q point or the quiescent point. So far, we've finished the problem by assuming it works in a certain section, and we verify its voltage and current value working in this section. This method finds the accurate section of the two sections. At the same time, the accurate quiescent point is also found.